All right. Why don't we get started? I know we have the banquet tonight, so we will end at 5:30. Anything we don't cover, we can take up tomorrow. So I'm going to talk about, in this one, instead of doing post-combustion capture, look at integrating capture with combustion. And there's basically two main approaches for this. One's called Oxy-Combustion capture, and the other's called Pre-Combustion capture. And pre-combustion capture is a lot associated with gasification technologies, even though not exclusively. So Oxy-Combustion capture, basically what we're saying here is we have our flue gas is a nitrogen CO2 separation, but if we can take the nitrogen out before the combustion process, then we have pretty pure CO2 coming out the end. There's water vapor with it, but that's easy to separate. But now we replace the nitrogen CO2 separation from the flue gas. We replace it with the oxygen separation from air up front. Studies have shown that this can be competitive with post-combustion capture at a coal-fired power plant, but because post-combustion capture is already established, for oxy-combustion to make indents, it has to show some significant advantages to have market penetration. And today there's very little field experience with oxy-combustion in power plants, but oxy-combustion in other industries is in use, and so can that be shifted over? So let's take a look at how this would work. Once again, we have a boiler, but instead of air going in, we're putting in oxygen. We do use air, but we have the air separation units. Once again, we have a steam cycle to make electricity, and our flue gas, we can clean it up and I'll go through some of the options of cleaning that up. And we have CO2. We don't need a separate CO2 recovery unit. But one thing is burning oxygen in a boiler is high temperature, and so a lot of times what they'll do is they'll recycle some of the flue gas in here and make basically a synthetic air mixture, so you can actually retrofit existing boilers with this to get the similar heat transfer characteristics in that boiler and make it acceptable without doing significant boiler changes if you're doing a retrofit. How does this work? Once again, we have our supercritical no capture plant at a 38.5% efficiency. We can maybe get a little increase due to the Oxyfuel combustion. The air separation unit is our biggest chunk of energy use, and that's all electricity. So we don't have to worry about integrating the steam cycle. The CO2 compressor, similar to before, and other pumps and blowers, similar to before. The key components that you look at is the oxygen production, boiler modifications, and the CO2 purification. So we'll look at each of those things. In oxygen production, today, cryogenic air separation is what's used for large scale. We can do 4,000 ton per day plants. The people have been working on improved ASU. Once again, exactly what oxygen purity you want is something to be determined. They like to have a little pressurized, basically a little over atmospheric pressure for the oxygen. We want low power, and we want large scale. So that's sort of the goals of what you'd like to see for an ASU for oxy-combustion power plant. There are ionic transport membranes that are at small scale, and they're not really competitive. People have, looked at these. When they first came out, there was a large buzz about what that can do, and the ultimate goal would say, okay, can we integrate this in a process? Because how these work is they work on oxygen partial pressure. So if you can sort of put it in the walls of a furnace and see the basically low oxygen partial pressure on the combustion side, you can almost have the oxygen coming in through the walls of the furnace at no cost. Unfortunately, to put that in practice has not been done yet, and I don't know if it can be because you have very hot temperatures in the furnace, but I think no one to date has really figured out how to incorporate these membranes into an oxy-combustion process. Oxy-boiler, so you're probably going to do the cryogenic. Oxy-boilers, I talked about synthetic air, basically the recycle of the flue gas. This was tested in the mid-'80s, and you can use basically minimum changes to the boiler with the right recycle ratio. The big question, of course, is air and leakage. If you get too much air and leakage, you defeat the whole purpose of using basically high purity oxygen in the boiler. And sometimes a lot of these boilers work at a little negative pressure for safety reasons, and therefore there's a good chance for air in leakage unless you really tighten up the boilers. And I'm going to show you the Vattenfall oxy-combustion. They was in France at Lac, Total used oxy burners as opposed to synthetic air. This is what's used in, they still had to recycle some air for temperature control, but oxy burners are used in the glass industry, metals, and other industries. Instead of Vattenfall, they mix the air and they mix the oxygen with the recycled air prior to going into the burner. And then people have looked at pure oxy boilers, eliminate the external recycle, maybe operate at pressure to avoid air leakage and have higher efficiencies. Once again, these don't exist. They have been research into it. I'm not sure. I haven't really seen anything about these recently. In terms of CO2 purification, the flue gas is typically 60% to 70% CO2. Most of the rest is water, but there may be some particulate matter that has to be removed. You have to basically adapt current types of end-of-pipe cleanup to do that. Of course, you have smaller volumes of air, so maybe that's easier. You can reduce the non-condensables in water can be removed during compression. The criteria pollutants, you have several options. You can co-sequester, in other words, keep it just when you pressurize, leave it in, and when you dispose of the CO2, you can have those go with it. That has some questions, on safety, on putting it through pipelines and putting it in the ground. So I don't know if that's an acceptable option. It's probably be the cheapest. Once again, you can modify current equipment. And also people have come up with interesting processes where you can remove during compression, when you remove the water and have them dissolve in the water and remove them as acids. If you want really high recovery, high purity systems, you can maybe put in a cryogenic distillation column or use some membranes to get you there. So these are things to look at, but as I say, we haven't really progressed that far. This was the biggest demonstration. I believe this was 2007 or 2008. Vattenfall, the Schwarze Pumpe plant in in Germany in the eastern section. This is the CO2 capture plant. It was, I think it was, 30 megawatts thermal. Here's a close-up view. Here's the boiler. So 30 megawatt thermal boiler. Here's the air separation plant to feed the oxygen in. They had a flue gas desulfurization unit. And then CO2 plant, basically what they did was liquefy the CO2, and you can see the liquid storage tanks that they put it in. A very successful demonstration. Unfortunately, they wanted to build a bigger plant, but unfortunately in Germany, they weren't allowed to because the German regulations made it very difficult to get rid of the CO2. An interesting thing, power plant, and this is for oxy firing on natural gas, is called the Net Power. This is a company that actually went public, I think at the end of last year. And they have I'll show you a picture of a demonstration plant that they had in Texas. And the way that this works is, so they have an air separation unit feeding into a combustor. It goes into a special turbine. We'll talk about the turbine in a minute. Then they have heat exchange, and then water separation. They cool it down, water separation. They remove, then they compress, and they remove some CO2, and then they recycle the rest. And they recycle about 97% of the CO2. So the bulk of the mass going through the turbine is recycled. And they have the cross heat exchanger, and that goes back into the combustor. So it's one thing is the big recycle that they have in the plant. And then, of course, critical pieces of equipment are the heat exchanger and the turbine. The turbine inlet pressure, so this is unlike other turbines, the turbine inlet pressure is about 300 bar, the outlet pressure about 30 bar. So keeping this at 30 bar means your compressor load is much lighter than if you started at atmospheric pressure. If we look at this on a thermodynamic chart, it's called the Aleb cycle after its inventor. And you can see here's the, here's going across the turbine where you're expanding it. Here's the heat exchange. You're cooling it down. This heat exchange here is going up here. This is the heat you get from combustion, from the combustor. And this is some area you need to add more heat. And they're actually doing that by recovering heat from the air separation unit, from the compressors in the air separation unit. And here's the compression going up, and that forms the cycle. So it's a fairly unique cycle. The original turbine in the plant was designed by Toshiba, but let me show you the plant. So here's a picture of the plant in Texas. I actually visited a couple times, but it's so long ago I can't remember where all the pieces of equipment are, but it's a fairly compact plant. So as I said, the original turbine was by Toshiba. There were some issues. They got it working, but there were some issues with the turbine and they needed redesigned. They're actually gone to a different manufacturer, and the turbines now are going to be produced by Baker Hughes. It's going to be, well, they have several signed contracts, of course, contingent on feed studies. So they have quite a few orders on their books. Now they just have to produce going ahead. As I say, they got a lot of capital in the company to help finance these plants through their public offering. And I think in the next year or so, we should be seeing some news, hopefully good news, but we should hear some news one way or another. Another area of interest with oxy-firing is oxy-fired cement kilns, and this has several applications. One of them, of course, is if we wanted to do cement plants instead of post-combustion capture on a cement kiln, we can try to do oxy-firing. Why does oxy-firing look interesting on a cement kiln? The studies have shown that on a coal-fired power plant, oxy-firing can be competitive with amines. And if we look at a coal plant, you need about 1.2 molecules of oxygen for each molecule of CO2 that's produced. The cost of post-combustion scales with the carbon dioxide. The cost of oxy-combustion will scale with the cost of the oxygen. If you look at a cement plant, because so much of the CO2 is created from the calcining of the limestone, that creates CO2, but it doesn't need any oxygen. You actually look at a cement plant that's fired with coal, you see that you only have about half a molecule of O2 per molecule of CO2. So that's much better economically than needing 1.2 molecules per molecule of CO2. Similar numbers for a gas plant here. So it looks like oxy-fire kilns can be very cost-effective in these plants. But oxy-fire cement kilns are not a mature technology. Once again, air leakage can be a big issue, especially in a kiln, even more so than a boiler. So these issues need to be resolved. When we talk about direct air capture, there's talk of oxy-firing kilns. So I'll revisit this tomorrow, because once again, if you're using carbonates, basically you're using strong bases, calcium hydroxide for direct air capture. Once again, you use a kiln to get that alkali. So this will be revisited tomorrow. So there's at least two major uses interested in. I do know researchers actively looking at this, and we'll just see where it goes. Another form of oxy-combustion is chemical looping technology. I first heard about this about 30 years ago, and the progress has been slow, let's say. But the idea is you're looping some sort of metal oxide. In this case, I show iron oxide. People have looked at calcium oxide because that's cheap. And you have two basically fluidized beds. One you put in the fuel, and what that's going to do is it's going to reduce the iron oxide. So it's going to reduce the iron oxide, so that takes energy. The fuel provides the energy, and since there's no air in here, you're coming out with pretty pure CO2. Over here, when you have the reduced iron, you react it with air, and it oxidizes the iron. It releases the energy, so here's where you recover the energy from, and here's where you get your flue gas going up the stack. So, one of the keys is finding a material that you can recycle basically thousands of times and make this work. So, on paper, this process looks wonderful. There's basically you're getting free oxygen. In reality, it's a very difficult design to do and to really make it work. And I know there was quite a lot of work going on this. I remember Alstom Power had a big, which is bought by Baker Hughes, had a big project on this. I know Gothenburg University up in Sweden had worked on this a lot. It was the Japanese, as a person from Japan that I first saw present this type of of things. So that's been out there a long time. It's, it hasn't been solved yet. So these are some, I'd say, highly technically different issues. And another form here is fuel cells. And I'm not going to go into detail here just because of the lack of time. But the fuel cells have the ability to keep the fuel stream and the oxygen stream separate. The way they do that is because of the electrolyte that gets transferred for the molten carbonate, that's a carbonate ion, so you can move the CO2 away from the oxygen. In a solid oxide fuel cell, it's the oxygen ion, so you can move that away from the CO2 part of it. I won't talk about implementation. Once again, these have been talked about for 30 plus years. There's been some progress, but the problems have not been solved getting this to work at scale, at least economically. So that's Oxy-Combustion. You can see there's a whole range of different variations that people are looking at to try to basically incorporate CO2 capture into the basic process as opposed to a add-on.
Can I ask a quick question on the Allen cycle?
Sure.
I mean, it's largely a closed cycle, right? Where they're just
Yeah, it's a closed cycle, right? It's basically a CO2 cycle in the turbine.
So how do you deal with contaminants? Like if the combustion process makes a little bit of junky out in the heat exchanger?
Good question. I don't have the real answer. I assume that they're going to have, if there's built up, they're going to have to put some sort of cleanup in there somewhere. At least with natural gas, I would think the worst thing is NOx. I don't know how big a NOx problem their turbine is, but.
Yeah, I mean, it won't because there's no nitrogen, right? So.
Yeah, I mean, there'll be, well, there's still going to be a little nitrogen in there.
Okay.
And you are going to have, you're not going to have 100% pure oxygen, and you're not going to have 100% combustion. I don't know. I'm sure they've looked at it, but I don't know the answer.
Yeah, the reason I'm asking is like we've had some projects on this, like one with Southwest Research Institute, diagnostics, if you could see it. They were like, the heck are you going to put that into our loop? Because there's just no way.
Yeah.
Okay.
So, yeah, I mean, you're absolutely right. And the problem with a lot of these processes is when you look at the nitty-gritty is the impurities. I am sure that I'm sure that where they're at in the development, they had a look at it, but I don't know what the solution is. So let's take a look at pre-combustion capture, and basically what we're trying to do is remove the CO2 before we put in combustion air that dilutes the product. So we don't want to have any dilution from combustion air. And in most cases, these processes will give you a pressurized feed. So I mean, like we saw in some of the hydrogen processes, that's technically a pre-combustion capture because we're not really, so it's a combination, like in the autothermal it was Oxy-Combustion, but in the, where they captured today, where they got the 60% out of the steam methane reforming, that was like a pre-combustion type of process. So I mean, that's really good, but the problem is is that there are costs with the process modifications, and we'll look at that with the coal gas. So if we're going to look at that, let's look at this in coal gasification. So you have modifications. Instead of using a boiler, using coal gasifier, you're going to have to, or if you're using methane, you're going to have to reform the methane. In both cases, you're going to need a water gas shift. So, as I say, the CO2 capture itself is cheaper, but, oops, the last thing, okay. So this, the process has not been proved cost-effective in the power sector, but you do use, if you look at ammonia, that's basically a pre-combustion capture process, even though, in that plant there's really no combustion, so it's, you don't have the combustion air in there, but it's very similar. You're capturing from a syngas. But let's take a look at a power plant. So we have an IGCC power plant. You have a gasifier, and what we're gasifying in is with oxygen. So we have an air separation unit. We get a syngas out of the gasifier. We clean it up and get a carbon monoxide hydrogen mixture. We put it through a combined cycle, make electricity, and have a flue gas. So this is your sort of standard coal gasification process. If we were going to add carbon capture to it, the front's the same, but now we're taking that CO hydrogen mixture and putting through a water gas shift. We're taking the energy out of the carbon monoxide, putting it into hydrogen. We're taking the carbon out of the carbon monoxide, putting into CO2. Then we can do carbon capture. This will be at pressure. This will be some sort of physical sorbent where we get the CO2 out and now have hydrogen that goes into a combined cycle turbine. If we look at the difference between this and a pulverized coal plant, you see that not only do we have higher carbon fractions, but we also have higher pressure and therefore much easier separation. If we look at the efficiency loss, once again starting with our 38.4% plant, the biggest loss here is in the water gas shift. So basically, we're basically boiling water with what this is, and it's a fairly significant amount doing it. We have CO2 compression, and the CO2 recovery part itself, which was the big part in the other plants, is very small here. And you have a little higher efficiency at the end than we had with post-combustion capture. You see the compression's a little smaller, and that's because when we regenerate at several pressure levels all above atmospheric, as you basically let the pressure down in stages, so you have higher pressure CO2 to start with to compress. Back in the day when carbon capture was, the DOE first started a program, the conventional wisdom that was, was that IGCC was the way to clean coal. Originally, before carbon capture, the idea was these gasification plants would have higher efficiency and they'll be able to handle the criteria pollutants easier, especially when they started talking about things like mercury. But what happened is, and then I was going to say what happened originally was the efficiency improvements never came because on paper they looked good, but plants weren't operable, and they had to back off on the efficiency improvements in order to get the plants to have high capacity factors. Then when CCS was involved, and also on the criteria pollutants, the technology got better on pulverized coal plants. So even though it's cheaper to get rid of the criteria pollutants on these plants here, it just wasn't a big enough difference to justify the extra cost of the pulverized coal plant. When carbon capture came, these gasifiers were rejuvenated, and it was assumed that this was going to be the way for the coal plants of the future. The problem, just again, was the high cost of the IGCC plant was a significant barrier. So it's easier to capture from it, but they never got the cost of an IGCC plant down such that the cost of IGC with capture was competitive with the cost of pulverized coal with capture. In the early 2000s, GE actually bought the Texaco gasifier, and they said they're going to bring it to the power industry. They wanted to get the capital cost within 10%, and they thought if they could do that they would be competitive, but that didn't happen. There were two, another challenge for IGCC was they were handling a wider variety of feedstocks. They can work on high rank coals, but they had trouble with low rank coals. That was sort of the impetus behind Southern Company's trig reactor, but there were bad experiences, both with the Southern Company at their Kemper County plant, which actually never ran, and at Edwardsport with Duke Energy, which used GE Texaco gasifier, but the costs were high, and it was very messy, and it ended up with a lot of lawsuits going on there. And I think these two experiences have just froze the utility industry, as well as other people, against going this gasification plant. So unless there's real improvement in the gasification technology, I think it's really dead in terms of coal gasification in the power industry. On natural gas, it's a little different story. As I said, I think I mentioned this earlier, that post-combustion capture was always the best approach for natural gas because it basically was targeted on the amount of CO2 you produced, the cost, and so you had lower amounts of CO2 here, so it was cost effective. But with renewables putting down capacity factors, it's hard to justify putting post-combustion capture on a gas plant and it's only operating, say, 50% of the time. But if we really wanted to decarbonize the electric sector and get natural gas out of there, we can put hydrogen in instead of the natural gas, and that hydrogen is made from methane reforming, which is called blue hydrogen. That's really a form of pre-combustion capture. So I think that's a way that maybe pre-combustion capture will get back into the power industry in the form of blue hydrogen. They are, as I said, I think mentioned already, that there's going to be hydrogen hubs, and one will be based on blue hydrogen and testing it out. There are, I'll go through, there are a couple demonstration projects like this that are being proposed. First, let me say that these technologies, I said we take the hydrogen and put it into a turbine, as I showed here, but those turbines don't exist to take pure hydrogen. There's issues with hydrogen. There's different energy density than methane. You have different flame velocities. You have to worry about flashback. But they're working on getting turbines to eventually go to 100% hydrogen. What they were going to do in these IGCC plants is, you notice there's this air separation unit here. So a byproduct of that air separation unit could be nitrogen. So when you separate out the oxygen, you get the nitrogen as a byproduct, and you can take that nitrogen and feed it into the turbine with hydrogen. So the hydrogen-nitrogen blend, standard turbines can take with the proper modifications to do it. So it wasn't a problem there. But now if we're going to go in with pure hydrogen, that's going to be another issue. There's been a project on the drawing board, and this is in the Netherlands. This was a plant that was originally a Vattenfall one. It was bought by RWE, and they say they're going to take one of these turbines and run on 100% hydrogen. Mitsubishi Power is going to provide the hydrogen for it. There's also another project in Texas from Entergy. This is a 1.2 gigawatt hydrogen-capable combined cycle power plant in Texas. They have approval from the PUC and is slated to begin this year and completed in 2026. And once again, they're going to be using Mitsubishi Power hydrogen-capable turbine train. So it shows you that these, at least people think hydrogen turbines, at least for gas, could be real. So once again, it's an interesting combustion issue on how you design these turbines and the like. So that's, I think, where a lot of the action today is on what I would call pre-combustion capture for power. So I'm going to end it there. And we have about 10 minutes for questions before we need to adjourn and get ready for the banquet tonight. Questions? So I'll say that I've been working, well, I started my first project in carbon capture 34 years ago, and the going's been slow. And, part of it is just the drivers, the policy drivers to do it. We haven't really decarbonized nearly as fast as at least the scientists want us to. So, but there's been a lot of, I say, progress on the technology front. We've learned a lot, but it's really at the stage here where we need to have real projects going ahead. As I mentioned earlier, there's over 160 projects in the pipeline that have been announced in one form or another. Unfortunately, it only takes a press release to announce a project. So some are at pretty early stages, but there is the interest there if the economics start looking good. In Europe, the situation's a little better than the US. They do have a emissions trading system. They have a $100 a ton price. Tomorrow I'll talk a little about the US with some of the tax credits. I mean, that's one thing that spurred a lot of these projects. That's not going to get us to the scale we need to, but it could get us to the next level from having a handful of these big projects, to maybe having a few dozen and have some learning from it and really understand what it's capable of doing and what technologies look good. So, but well, if there's no questions, we'll see everybody tonight at the banquet. And I'll be up here for a few minutes if anybody wants to ask something individually. Thank you.